Good evening, guys. So, we are presenting the bracket assignment problem for NCAA men's basketball tournament, which shows how a mixed integer linear programming problem is solved. This is presented by Ravan Akhtar, Simon Pastrana, Priya Ranjan Sontanke, and Yash Samani. So, first, I'll be speaking about how the tournament is structured. It is a single elimination tournament. The main tournament contains 64 teams, and the teams that lose go out of the tournament. Secondly, the seeding and the ranking. So teams are seeded according to their performance during the season, with a higher seeded teams match against the lower seeded teams in the initial rounds. There are regional competitions. So basically, the tournament is divided into four regional competitions, each culminating into a regional champion. And the winner of these four regions advance to the final rounds. The final rounds means the final four, which narrows it down to the semi-finals and the finals, which is held in a predetermined championship location. And the winner of this is crowned as the national champion. Now I'll be speaking about what the purpose of the paper is. So as we can see, there are four purposes from which we can derive from this paper. The first one being optimizing travel and costs. So the paper seeks to address the issue of assigning teams to opening round locations in a way that minimizes travel time and costs for both teams and fans involved in the tournament. The second one being fair competition. So it aims to create a more equitable and balanced bracket for the teams, ensuring that the process is unbiased and fair, with a particular focus on how the seeding and the location can affect both the team and the fans' experiences. Operational research application. So from the paper, it is proposed that a mathematical programming approach should be taken to the bracket assignment problem, demonstrating how operations research techniques can be applied to sports scheduling. The last one being improvement over existing methods. So the paper shows current practices and presents a new model that could potentially offer a better method of scheduling tournament games and improving upon the limitations of the previous methods.
After understanding the structure of the tournament as well as the purpose of the project and the paper we want, I'm going to talk about the variables that comprise the whole objective function. The variables are first the T, which stands the teams in the tournament. As mentioned before, there are 64 teams, so the range is from 1 to 64. The second variable will be J, which is basically the first round locations to which the pods are to be assigned. 1 to 8. There are 8 first round locations in total. The third is the seeds, which is denoted by the letter S. They are 16 seeds. And the fourth is the pods, which are 16 pods in the whole tournament. The R are the regional sites. As mentioned, there are 4 regional sites in the whole tournament. And then we're going to talk about some variables that are composed of other variables. In this case, the DTJ, which is the distance from the team to a location. The TR is the expected travel costs associated with the assignment of a team to a regional site. Lambda TS is a receiving penalty for improved travel cost. This is when a team wants to accept the reseeding of the position in the tournament, or they don't want to accept it. They are going to have a penalty and a cost insured. And C, which denotes the designated teams conference. Now that we talk about the variables, I would like to talk about the decision variables that will be applied in this model. These decision variables are 3, and all of them are binary variables. In this case, XTRS is equal to 1 if a team is assigned to a region as a seed number, or 0 otherwise. QPJ equal to 1 if pod is assigned to a first round location, and WTJ equal to 1 if a team is assigned to a first round location, and 0 otherwise.
All right, so this is the objective function in the model. The first part of it is minimizing cost. More specifically, it's minimizing the cost of first round travel costs. expected second round travel cost, and the penalty that is associated with reseeding a team that Simone talked about. The reason that we're minimizing the expected second round travel cost is because only half of the teams make it to the second round. So that cost is based on probability given historical, given how the tournament turned out in the past. The second part is to minimize the distance traveled. The model wants to minimize the distance to every team's first round location assignment. So next, I'll talk about the constraints in the model. The constraints largely revolve around making sure that every team is placed in an appropriate pod, region, seed, and first round location. So first, the model ensures that this constraint ensures that each team is assigned to a region seed pair and vice versa. Second, the model assigns each pod to a single location and assigns each location to 2 pods. Next slide, please. Thirdly, we need to ensure that each region seed pair is assigned to a pod, and a pod is assigned to a first round location as well. And lastly, we need to make sure that if multiple teams make the tournament from the same conference, they should not be placed in the same region. And then we need to prevent those intra-conference matchups until the 4th round.
So here we look at other way to solve this problem. Now this is called summation team assignment. Compared to the previous one, which is minimax team assignment, this model overcomes the deficiencies of first model, which is MTA provides weak linear regressions. And the second problem with the previous model was that it was having minimax constraints. We are replacing this minimax constraints with a minisum formulation. So as we can see, the objective function is the same as explained by Raman, where we have to minimize the cost and minimize the distance. The only difference is instead of W, we are using U. So now let's look at the constraints. So here we are using UTPJ, which means that we have to ensure that each team is assigned to a pod and each pod is assigned to a location. And then we have other 2 constraints where we have to ensure that each team is assigned to one first round location and each first round location is receiving 8 teams. And following those constraints, there are some more. So we have to ensure that each team is assigned to a region seed pair. We also have to ensure that each region and seed is assigned to a team. And we also have to ensure that each pod is assigned to a location and each location is assigned to pods. And we also have to ensure that if top seeds from same conference make to the tournament, they will not be placed in the same region. We also have to ensure that no intra-conference games occur before the 4th round. And finally, we have to ensure that each team is assigned to one pod first round location pair. We also have to ensure that 4 pairs of teams and first round locations are assigned to each pod. And we also have to ensure that each 8 pair of teams and pods are to be assigned to each first round location.
So to conclude, the model does indeed work at a reasonable pace, but only if the NCAA committee themselves decide the assignments for seeds 1 through 4 for each region. Given that, the model does successfully assign teams given the numerous constraints. But it also seems like every few years the NCAA adds more constraints. So one example is BYU, which is a religious school. They are not permitted to play on Sundays for religious reasons. So additional constraints can be and will be added to this model in the future. This model can also be used for other collegiate tournaments. For example, the women's basketball tournament, they do have different constraints, but by adjusting it, the model will work as well. It can also work for different types of sports tournaments as well, but the number of teams, the pods, and all that will need to be adjusted. Thank you for your time, and we hope you learned a little bit more about the NCAA men's basketball tournament.
Thank you.
Thank you.